Hey everybody, so this week we are going to start going through gait analysis. So gait analysis, what we're going to do is we're going to take all the variables and concepts that we've talked about so far, kinetic concepts like kinematic concepts like angular velocity, kinetic concepts like angular momentum, equilibrium, torque. We're going to take all those concepts that we've talked about and we're going to apply them to how the joints move in a series, in a sequence of muscular contractions to allow us to walk. As we get into the lectures, what I would like you to do is to obviously pay attention and start thinking about what you would like to measure in your gait analysis project. Now, you've already written your introduction, your methods, so you have a really good idea of where your project is going. This week, when we start talking about gait analysis, I'm going to introduce a lot of different things to you guys, specifically the phases of gait and the gait cycle, and you're going to have a really in-depth view of the specific parts of the gait cycle that you might want to measure in your project. So what is gait? It's a style of walking or running, and everyone's gait is different. It may not look that way, and most human beings walk very similarly, especially if they don't have any clinical conditions or injuries, but everyone has subtleties to their gait that makes it just a little bit different than someone else. It's like your fingerprint. If you couldn't take someone's fingerprint, taking a measure of how they walk over time and saving that image and then comparing it as they get older would be a great way to identify someone, because everyone's gait is just a little bit different. It's a method of locomotion or moving us forward. What is normal versus abnormal gait? Normal gait is not having to create compensations to be able to efficiently move yourself forward. So the human body is always going to want to do things as efficiently as possible. And what does that mean? With as little energy expenditure as possible, right? So with the smallest VO2 possible. So we get in better shape. Obviously, if I work out over a period of 8 weeks, then I might be able to run on the treadmill at a lower VO2 than I could 8 weeks ago, right? Well, gait is the same way. You're going to walk and you're going to find the most efficient way to walk. And if you're not hurt, you're not injured, you don't have any clinical conditions, you're going to be really efficient when you walk. All the muscular contractions that have to happen in the order that they happen will not require a ton of energy expenditure. But if you are injured, if you do have some sort of clinical condition that affects your gait, like cerebral palsy or multiple sclerosis or muscular dystrophy, if you have something going on like that, what your body is going to do is it's going to create compensations. It's going to want to complete the gait cycle. It's going to want, your body is going to want you to move forward. So that might start to look a little bit different. You might have to bend over at the waist a little bit, or you might have to rotate your trunk a little bit more to be able to swing your legs through. If your muscles don't work in the way they're supposed to, your body's going to find ways to compensate for that. It's going to turn different muscles on more if other ones aren't doing their job, right? So when we're talking about normal versus abnormal gait, we're talking about what's normal for you. And are you displaying normal gait today, or has something happened to change that? One thing that can actually change that is just exercise in general, especially if you're starting like a new exercise program or you're increasing the intensity of your exercise program. What might happen? You might get sore. And if you're sore enough and you have enough delayed onset muscle soreness, remember that's caused by trauma to the microscopic muscle tissue. The actin and myosin and the sarcomeres get really broken up. So the mechanical advantage that you have by connecting actin to myosin and making those cross bridges has been diminished. So I think a lot of you know that after a really hard workout, you might walk funny the next couple days. And that would probably be considered abnormal gait for you, because you're going to have to create compensations to be able to complete the gait cycle and move yourself forward. So how do we measure gait? If we're using technology and we're measuring gait quantitatively using numbers, like we have been with Kenovia this semester, there are three that we can use in conjunction with one another to get valuable quantitative data about gait: motion capture, force platforms, and electromyography, or EMG. Motion capture is what we've been doing with Kenovia. You can use one camera or a series of cameras to watch how specific joints move and gather kinematic data, right? So motion capture is all about kinematic data. Kinematic. What is it? Kinematic? Jeez. Kinematic data. Motion capture is all about kinematic data. Angular velocity. Angles at the joints. Step length or stride length. We'll talk about the difference between those two. How many steps you're taking in a minute. Your cadence. How high your hips are off the ground. That's all kinematic. That's all kinematic data. Stuff that we can measure with our eyes and with measuring distance. Now, we can combine that by watching someone kinematically with motion capture. And at the same time, we can gather kinetic data. How much force is being put into the ground at certain angles. So if you're watching someone walk or run or jump, and you're saying, okay, their knee is at this angle right now, how much force is being put into the ground versus 3 seconds later when their knee is at a different angle. So motion capture and force platforms allow us to get kinematic and kinetic data at the same time, which is really valuable. And the last tool that we use when we're gathering quantitative data would be electromyography, or EMG. And that's what you see here. All these little wires that are hooked up to the legs, right? Those are called electromyographic electrodes. I got it. Electromyographic electrodes, EMG. Let's just say EMG. That's easier for me today, I guess. So EMG is a way for us to measure the electrical activity of the muscle tissue, the action potentials, just like we do with ECG, right? So if we have motion capture, kinematic data, force platforms, kinetic data, EMG, data on how the muscles are turning on and how they're activating. Now we have a three-pronged method to look and see exactly what's happening at the joints in any period of time that we want to measure. And this is the most basic setup for most biomechanics labs. So in our lab, we have all three of these things, okay? In more advanced biomechanics labs, they use them all at the exact same time and gather that data at the same time. Now, what if you're in a setup where you don't have the ability to get quantitative data, or you don't necessarily want to get quantitative data? Setting folks up in a biomechanics lab and putting markers on their body and getting the cameras set up and getting the force plates set up, that all takes time. And if you are a physical therapist or an occupational therapist or an athletic trainer, you might not have the time to set, in like a 30 or a 60-minute session, you might have the time to set someone up to gather all that quantitative data. So another valuable tool is subjective, observational, qualitative evaluation of gait. And that's basically using a sheet like this and doing observational gait analysis. And what that involves is just a scoring mechanism for different areas of gait. So you would necessarily, the best thing to do would to have a baseline of this before you measured someone after they had a surgery or after an injury or something like that. Is the shortened swing phase present? We'll talk about what that means. What about their step width? Is that increased or decreased? Foot angle, cadence, how fast are they taking steps? right? Is their trunk, what's the position of someone's trunk? Are they really leaning over? Are they really leaning back? What about their pelvis and their hip and their knee placement? And you would go through and you would watch someone. And a lot of clinics and labs, what they'll do if they're using observational gait analysis, they will videotape someone at the bare minimum so they can go back and the clinician can watch and rewatch and score their gait just by using their eyes. Now, one thing to keep in mind is doing both quantitative gait evaluation with technology and observational or qualitative gait analysis. If you do both and you're really good you've practiced observational gait analysis, qualitative evaluation, if you're really good at that, you've been doing it for a long time, your evaluation on a paper like this should be supported by quantitative data that we would get from the technology side of things. Where would we apply the information that we get from qualitative or quantitative gait analysis? We would use it in hospitals with clinical populations, folks that have clinical conditions that affect their gait. I'm going to try not to sneeze. Hold on. Woo. Sports performance. So anomalies or compensations in gait are going to affect someone's performance. If someone has some sort of compensation where they lift their hips up a little too high on one side, or they have a leg length discrepancy, like one leg is a little bit longer, that might affect their performance on the field. Rehab. Obviously, we want to get someone back to being as efficient as possible. So if you have an ACL surgery, if you have you got a sprained ankle or something like that, that's going to affect your gait and cause you to develop compensations in your gait that you want to try and work through in rehab so that your gait gets back to normal and you become more efficient. And then lastly, prosthetics. Prosthetic design is huge in conjunction with gait analysis. So a prosthetic design is meant to work with the specific human being, and you put the prosthetic on the human being and you watch them walk. And you're going to measure their gait. More often than not, when a prosthetic is being designed, they're going to use quantitative evaluation of gait. They're going to use the technology to make sure that the fit is as perfect as it can be so that there's no compensations that you have to build when you put that prosthetic device on the leg. So let's go ahead and look at the gait cycle. When we're talking about the gait cycle, it's important to remember that for this instance, when we're watching this gait cycle here, we're looking at the right leg, the leg that's closest to us in the sagittal plane. So the gait cycle measures the movement of one leg through a period of time. And it starts off with a series of movement patterns that we track over the right leg. It starts off with an initial contact and goes through what's called the stance phase, where the right leg is in contact with the ground and the right leg musculature is now in charge of kinetically applying force to the ground with friction and muscular force and moving the left leg past the right leg until we get the left leg in contact with the ground. And now we're into what's called swing phase for the right leg. Remember, it's all about the right leg in this instance. If you were walking the opposite direction, we'd be tracking the left leg. And the swing phase is what it sounds like. It's where the right leg is going to come off the ground and start swinging in midair to pass the left leg again. And this is one full gait cycle. Heel strike to right leg, all the way back to heel strike to right leg. And that is one full gait cycle, okay? Now this was in some of your reading, and I do like this graphic. I like combining it with the previous one because this one gets into a little bit more detail about the position of the leg, especially during swing phase. And we'll talk about this in a little bit more detail, but you can see that as we look at the swing phase in particular, pre-swing, initial swing, mid-swing, and we can go back and we can look pre-swing, initial and mid, and terminal swing. So this graphic right here kind of combines initial and mid-swing, whereas this one, pre-swing, initial, and mid, they're a little bit separate. And they kind of separate out the movement of the leg during the swing phase with a couple in particular: toe off, feet adjacent, and tibia vertical. So feet adjacent means that the 2 feet are right next to one another. Adjacent means next to one another. Then we have tibia vertical, where that's exactly like it sounds. In the swing phase, again, we're looking at the right leg here, the highlighted leg, or the gray leg. The tibia is now vertical. It is swinging forward past that left leg, and it's getting ready to contact the ground again. So I like both of these graphics in conjunction with one another, and I suggest as you're studying, you use them both to help you piece through the phases of gait. Okay, so I've basically described to you that gait is a cycle combined of stance phase and swing phase, right? So the stance phase and the swing phase combine to make the entire gait cycle for one leg. We're always looking at one leg. So most of the literature and most of the graphics that you're going to interact with in this lecture and in gait analysis are going to show someone walking this direction, walking in front of you with their right leg closest to you, okay? Just remember, if that person was walking back the opposite direction when we were doing gait analysis, we would do it on their left leg. And a lot of times when we're doing the gait analysis, we'll look at the right leg going one way, and then they'll turn around and we'll look at the left leg. We'll do gait analysis on both. A lot of times gait analysis is done on both sides of the body. Just when we look at graphics and we're talking specifically about the gait cycle, we're going to look at usually the right leg. That's just how most things are written. One thing to take into consideration when we're talking about the gait cycle, it's broken down most often when we're looking at graphics like this one and we're reading about it, it's broken down into percentages. So when we get from A all the way to G, we are at 100% of the gait cycle. We've completed the entire gait cycle, 100%. We've gone from heel strike, right leg, all the way back to heel contact or heel strike again on the right leg. That's 100%. So really, to have a really good understanding of the gait, it's good to know what periods of the gait cycle make up percentages. Let's start with stance and swing. The stance phase for this right leg will, in most normal gait, comprise 60% of the entire gait cycle, whereas the swing phase will comprise 40%. Now, there are two other subphases, and they should be down a little bit lower here, but if we look at double support versus single support, double support and single support are easy. Just remember, double support, 2 feet on the ground. Single support, 1 foot off the ground. You're supporting on one leg. Single support is supporting on one leg. Double support is both legs are on the ground. And during stance phase and swing phase, we're going to have double and single support, right? During the stance phase of the right leg, the single support is going to be over the right leg. In the swing phase, single support is the left leg as the right leg is swinging. Now, if you look at the percentage of time when we're in double support versus single support in each phase, when we're talking about the right leg in particular, and we're in the stance phase, when we're in the stance phase, we're in single support 40% of the time and double support only 10% of the time. So the stance phase is exactly like it sounds if you break down the percentages. We're only in single support or we're in single support a lot during the stance phase. When we're in the swing phase, we are in single support on the left leg quite a bit, and we're swinging the right leg. So if you look at the gait cycle and you look at the period of time, this is a big takeaway here. If you look at the period of time where we're in double support, where we have both feet on the ground, and the period of time where we have one leg off the ground and we're supporting ourselves, we are in single support quite a bit in both phases. And that should be a big takeaway, because what happens when we're on one leg? A lot of muscular activity has to happen to keep us balanced, to keep our equilibrium in check so that we don't fall over. Obviously, these percentages are for just normal walking. They're going to shorten if you start walking faster. The percentages get bigger or smaller depending on how quickly you're walking. A couple other pieces of terminology. If we're talking about foot placement, stride length, the distance between two successive placements of the same foot. Stride length is heel strike, right leg, to heel strike, right leg. Stride length is the same thing as 100% of the gait cycle. So if we complete one gait cycle, right? If we complete one gait cycle, then we've completed one stride. 100% of the gait cycle is one stride. So we've got heel strike, right leg. If this is the right leg, heel strike, right leg, over to heel strike, right leg. That's one stride. Step length is the distance between your left and your right legs. So step length, step length, step length. When you have someone who has pathological or abnormal gait, some type of condition that's affecting their gait and causing compensations, you're going to see different step lengths, especially considering which side of the body you're looking at. So they typically, most folks who have a normal, non-compensated or non-pathological gait are going to have fairly consistent step lengths. If you have pathological gait, you're going to start seeing variations in step length. So a couple other pieces that we have to consider when we're looking at gait analysis. What about the walking base or the width of strides, right? So let's go ahead and take a look at this graphic. So when we look at stride width, which we can also call the walking base, right? We can also call the base of gait. How far apart are the feet? We start looking at how far apart the steps are and how far apart the feet are when someone completes one full stride. And why is that really important? Well, one thing to take into consideration is as our feet get wider, what happens? We've already talked about this. It's your base of support. Remember, we talked about base of support and how low or high your center of gravity is when you're walking. So when someone gets older or someone has a pathological gait, an abnormal gait, but particularly when you talk about as people get older and older and older, what do? They start taking wider steps, and their stride width gets wider. That creates a larger base of support that moves their center of gravity closer to the earth and makes them more stable so that they don't have to worry about falling as much. Another thing that you can look at when you're measuring stride width, compensation that someone might make when they're walking is toe in or toe out. That has a lot to do with the different types of muscles that are firing and what is being required when the foot touches the ground, particularly in pathological gait. So when we're looking at the width or the base of support, we can measure, is the toe in, is the toe out? Cadence, number of steps per minute, number of steps you take in 60 seconds. That's cadence. Stride time is 120 divided by your cadence. Now, why is it 120? Because one full stride or one completion of the gait cycle relies on you using 2 legs, right? So if we take your stride time, you want to do 120, that's 60 seconds per leg, divided by the number of steps you took in 60 seconds. And then speed, if you remember this from kinematics, when we went over angular and linear kinematics, we talked about stride length and stride frequency. The length of someone's stride, right? The length of someone's stride, now that's not the width, that's the length. How long is someone's stride, right? So how long is someone's stride divided by stride time? That's going to dictate how fast someone is moving. So as far as pathological gait is concerned, we look at a few things. Step length may shorten. Support time, so support time discrepancy. So you might actually see a lot more double support in a pathological gait, slower walking speeds, and normalization. So trying to battle the body into a more efficient gait, and the abnormal gait becomes their normal gait. So what we're going to talk about now is some of the kinematic and kinetic components of the gait cycle. So we're going to bring in some of the concepts that we talked about earlier in the semester, and we're going to apply them to specific components of the gait cycle. And the meaningfulness of these concepts, I hope, will really link up with you in exactly how we accomplish this series of movements that allows us to move through the gait cycle. First thing that I want to bring up is when we're looking at a lot of the data on the next few slides, and from some studies that have been done on the gait cycle, you're going to see the word moment quite a bit, joint moment. That's the same as torque, newtons times meters, okay? It describes the force applied at the joint. So anytime there is muscular force involved, more often than not, it's going to cause a torque to rotate around another body part around the joint, right? So if we look at this really simple graph and we look at percentage of the gait cycle, we're going to have extension of a joint and flexion of a joint. This could be any joint in the human body. It could be the knee, it could be the hip, it could be the elbow, right? If we have extension, if we have flexion, and this right here is measuring support moment, which means force absorption during whatever phase of the gait cycle we're looking at. So this is a pretty simple one. We're going to have some more detailed graphs and charts on the next few slides. So the biggest thing for you to do is to take a look at the independent variable, the dependent variables, and there are descriptions on each of the slides. And these were in your reading too, so if they're super confusing or what I'm saying just doesn't make sense, you can always go back to the reading and get a more thorough understanding of what the graphs mean. So let's take a look at this first one. And let's go ahead and break it down. We're going to talk about joint angles at specific joints during the gait cycle. So the first thing that we will want to do is we will want to take a look at the description, sagittal plane joint angles. So we're sagittal plane, right? Just like we've been talking about, in degrees during a single gait cycle. So heel strike to heel strike of the right hip. And it's actually telling you that when the right hip is in flexion, when the right hip is flexing, right, or the knee's coming up towards you, that's going to be positive. Knee and flexion will be positive there. So when you're pulling your ankle to your butt, that would be represented as positive on the graph. Ankle, dorsiflexion is positive, right? So when the toe's coming up towards the shin in dorsiflexion, that would be positive on this graph. And then you have so we're looking at the hip, the knee, and the ankle. That's all we're looking at. Down here, your independent, what we're controlling for is the gait cycle. So from 0%, which would be initial contact, all the way over to 100%, which would be back to initial contact again. And then we have the different parts of the gait cycle. Initial contact here, opposite toe off, which would be, in this instance, if we're looking at the right leg, that would be the left leg toe off. Heel raise of the opposite leg, right? Heel raise, we're still in stance phase here. We're in what would be transitioning to terminal stance. And then we have opposite initial contact, right? Opposite initial contact, toe off, feet adjacent, tibia vertical, feet adjacent, tibia vertical, back to initial contact. And then you have the phases of the gait here. So we're going to measure joint angles in degrees. So let's start down at the bottom with the ankle. So remember, dorsiflexion will be positive, plantar flexion will be negative. So let's look at initial contact, right? Let's look at initial contact. Initial contact, we don't have a whole lot of joint movement going into opposite toe off, where we look at, and this is also considered the rocker joint or the rocker position, where the ankle, you look at joint angle, when you make initial contact, you got a heel strike into the ground, and then you start going into plantar flexion, which makes sense, right? You're going to go into plantar flexion, and then as you start gumming over that single leg, what's starting to happen? You make contact with the ground, and now the tibia and the fibula start to move forward a little bit. You're going into some dorsiflexion, dorsiflexion, dorsiflexion. You've gone into single support on that right leg, and then boom, toe off. Big, so you've rotated a little bit, and then you've recovered, plantar flexion, toe off, right? So then we recover, and we go back into feet adjacent. Feet adjacent, we're here, right? And in order to clear the ground, if your toe was dropped, your toe would hit the ground. You're going to have to come into some dorsiflexion again, land on the ground, and it starts all over again. Do that for every single joint, right? If we look at the knee, remember it says knee flexion is positive. Knee flexion is positive. So knee flexion, right? Extension, flexion. Extension, flexion. So if we look at knee flexion during initial contact, this should make sense, right? So we have some initial knee flexion. Unless you're landing with a hard extended knee, you're going to have some initial flexion, right? And then we move through opposite toe off, right, of the opposite leg. We're starting to extend our leg now. We're starting to extend the knee to stand up on the leg, the support leg. So remember, this is the right leg, right? We've made contact. So you made contact, right? Let's look at my leg here. When you initially make contact with your leg, I'll use my left leg here, but remember, we're talking about the right leg on the graph. When I make contact with the ground, I'm going to flex just a little bit. Then I'm going to start moving over the leg. I'm going to move over the leg, and I'm going to extend to start standing up over that leg, right? So as you move through the gait cycle, you're going to start to extend, right? We're going to start to extend. And then, right, when we start to get into toe off, let's start looking at toe off, right? We're start looking at toe off. We're getting some flexion, right? Because we have extended, look, we have extended all the way to stand our body up into toe off, and then we start flexing the knee again. Why do we start flexing the knee again? Well, because now we're getting into swing phase. Swing phase, we have to pick our leg up to swing it through, right? So we have to flex. We're going to flex it big time. We're going to swing it through, and then we're going to start to extend it out in front of us to land on that heel again, okay? Do the exact same thing with the hip, right? So how much extension and flexion, look, we have this steady drop in hip extension, right? So when we are in our initial contact, right, we're in a little bit of hip flexion. Remember, flexion is the knee coming up towards you at the hip. So we're in a little bit of flexion as we start to move into our toe off, as we start to get into our mid stance, right? We are starting to, when we get into mid stance and I'm on that right leg and I'm starting to move towards single support, I'm going to have to stand up, right? I'm going to have to move my center of gravity up so I can stand up over the leg and I can swing the other leg through. So I start to extend at the hip. Lots of glute max activation here. So I'm going to start to extend my hip and I'm going to start to stand up, right? And then I'm going to, once I'm into the swing phase, I have to flex the hip again. So remember we're looking at that initial contact with the ground, right? A little bit of hip flexion so I can absorb the force. If this is my hip, flexion, extension, extension, flexion. So I drop into my initial contact, right? And then I start to absorb the force a little bit. So some flexion, and then I move over the leg. I'm starting to stand onto the leg, and I have to extend upwards, right? And then I move over the opposite leg. I get the opposite leg on the ground, and then I've extended. So I raise myself up. I got my opposite leg over, and now I have to go into swing phase. And I have to start to flex the hip again. Flex, 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 so I can pick it up. Flexion and extension. Now, I went into quite a bit of detail there, so I want you to have a good idea of where we're going with these graphs on the next couple slides, and that's how we do it, right? This one was particularly about joint angles throughout the different phases of gait. And once you break it down, it makes quite a bit of sense. If you ever get confused, just go back to your graph, okay? So I'm in mid stance. All right, I'm in mid stance here. In mid stance, that mid stance is right between opposite toe off, that's opposite toe off of the other leg, and heel rise of the leg that we're looking at, the right leg. So that would mean that the hip is in some flexion and the knee is in some flexion, right? And it's getting ready to start extending. And then the ankle is, there's not a whole lot happening at the ankle, all right? So hopefully that makes sense, and we'll go ahead and move forward, and we will talk more about joint angles. This is the same thing that we just looked at, okay? This is the same thing we just looked at, only broken down into the hip in flexion and extension, the knee, flexion and extension, and the ankle, flexion and extension. Okay, so if we're looking at the joint angles here, this is just another way to look at it. It's breaking it down into just separate graphs. So you can look at that too to get a better idea of what's happening during the gait cycle, all right? Okay, joint torques. Now, when we start talking about torque, we're talking about muscular activity, all right? So when we talk about joint torques, we're not necessarily talking about electrical activity being measured at the joints or at the muscles. We're talking about how much force is being applied at the joints with torque. So you can't necessarily measure torque directly in the muscles, because you would have to open the body up and measure how far away the origins and insertions are from the joints, and would have to measure the amount of force that's being applied in real time, and you just can't do that. But since we've been able to look at cadavers and we know usually how far away joint insertions are, they have been able to get a really, really good idea of how much torque is applied at the joints. So we can break down the phases of gait and look at how much torque or moments are being applied during the gait cycle. So if we have the sagittal plane, let's look at our description here. Sagittal plane internal joint moments, Newton meters per kilogram of body mass. So that makes sense. Newtons times meters is torque per kilogram of body mass. So what that means is it's taking whatever body mass you have, how much torque is being applied per kilogram, kind of like we do with VO2, right? So we're looking at a single gait cycle of the right hip. Extension is going to be positive. So anytime there is, let me get out my guy here. This might be easier. So if we're talking about an extension moment, right? We're talking about extension. There's hip flexion, hip extension, right? Try and keep it in the socket, right? Hip flexion, hip extension. So if we're talking about an extension moment, what we're talking about is gluteus maximus activation. Extension moment or extension torque would be the glute max pulling the hip into extension, okay? So when we're looking at the hip, extensor moment or extension would be positive on the graph. The knee extension is going to be positive, and the ankle plantar flexor moment is positive, okay? So if we're looking at the amount of torque required to get us through the different phases of gait, why don't we start with something? I always like to start with toe off because that is pretty indicative of what's going to be happening. And so let's think about toe off. Let's start here just as an example. Get a drink. All right, so if we start looking at toe off and we start looking at the hip, let's go ahead and look at the hip during toe off. Okay, so if we're looking at toe off, you're like, okay, wait a minute. Why does it say flexion? Why does it say flexion at toe off? Because if you're going into toe off, right? We're going into toe off, we should be really extending the hip into toe off, right? Right? Well, that's weird. Why is there a big flexion? Why is there a big flexion moment during toe off? And this is where our understanding of levers and torque really come in handy. Okay? Remember, there's two types of muscular contractions. There's concentric and eccentric, right? So if there is a big flexion moment during hip extension, okay, what's happening is if I am in toe off, right? Can't really see my toe, but if I'm walking over this leg and I'm going into toe off and I'm really squeezing my butt hard to get to that toe off while I walk, well, there's a big torque in my hip flexor, right? There is a big torque in my hip flexor. Why? Because as I start to do this, where is there an eccentric contraction? In the hip flexor. And that is why during toe off, there's actually a bigger torque in the hip flexor that's showing up because we have an eccentric contraction that's happening here and a concentric contraction that's happening here, okay? So when we start looking at moments and torques, a lot of times the bigger moments and torques show up during the eccentric phase of the contractions. So if we look at, let's go back to the hip, we've done toe off, let's look at initial contact, right? And you're thinking, wait a minute, hip extension, right? Because if you look all the way over the graph, hip extension. hip extension during initial contact. But look at initial contact, right? Look at the position of the foot. If you just imagine yourself walking, you wouldn't be in hip extension, right? Right? You would be in a little bit of flexion, right? But as you land on the ground, right, in order for you not to collapse on yourself, your glute max has to really contract into hip extension so you can land, right? So you are getting a little bit of flexion, right? But the overriding torque is hip extension so that you can land and so that you can balance out the two joint torques. So when you have that initial contact with the ground, right? And right now I'm heel striking into the ground, right? I'm going to start absorbing the force, and my glute max is going to try and extend my hip while my force of gravity is coming, and the other side is going to go into flexion. So the biggest torque, or the biggest moment, I know it looks like I'm rubbing my butt, right? But the biggest torque or the biggest moment is trying to keep control of the flexion, and the way you do that is a big torque on the opposite side of extension. So hopefully that makes sense, especially at the hip. That can be a little bit confusing. What we're looking at here is eccentric contractions, right? We're looking at eccentric contractions, and those create moments or torques. Now, concentric contraction creates a torque too. But when we're looking at this, we're looking at where is the most torque and where the biggest moments being created during the gait cycle. And so during initial contact, yeah, you're falling into your foot, right? You're starting to fall into your foot, and your knee's going to flex, and your knee's going to flex, and so is your hip. But that's not where the biggest amount of torque is. The biggest amount of torque is on the opposite side. So instead of there being a really big hip flexion, there is a hip flexion, but the biggest torque is on the back side of the body to make sure it controls for that hip flexion, and that would be extension. I want you to think about this, because look at the knee too. Look at the knee, right? When you get into initial contact, right? You get into initial contact, you have some flexion, some force absorption, but immediately you're starting to get that extension, right? So you have to think that if I landed on my foot when I'm walking, if I landed on my foot while I'm walking, if my hamstrings, I'm landing, right, and my knee starts to go forward a little bit, if my hamstrings didn't contract, right, I would just fall forward, right? Because my quadriceps are really in charge of extension, and when I start to fall forward a little bit, my quadriceps start to contract to make sure that my knee doesn't fall forward, and my hamstrings also contract to make sure that my knee flexes enough to absorb the impact. So both sides of the joints, both sides of the hip, both sides of the knee, both sides of the ankle, the muscle groups, this is where the agonist and antagonistic muscle group activation, right? So biceps, if I'm doing a curl, agonist. The triceps is the antagonist, right? This is where concentric versus eccentric contractions come into play big time when you're talking about joint torques during the gait cycle. If we did not have opposing muscle groups, we wouldn't be able to move. Every step we would take, we'd fold up like a worm, right? So something to kind of keep in mind when we talk about joint torques. Now, let's look at joint power. So let's take a look at joint power. Now, we have to remind ourselves what that means, right? So power is work over time, right? Let's kind of remind ourselves a little bit here. Work equals force times distance. And then power equals work over time. Right? So if we remember what those two are, then it's a little bit easier for us to sort of conceptualize what it means when we say joint power. Right? When we say joint power, we're talking about the amount of work that a joint does in the amount of time. And so when we talk about joints, we typically talk about angular distance. So the greater the amount of distance that's covered and the amount of force that's applied, or torque, because we're talking about a joint in a certain amount of time, will develop power. So let's take a look at what this chart is telling us. And again, we're going through the different parts of the gait cycle here that match up with our graphic over here. Sagittal plane joint powers, watts per kilogram of body mass, okay? So we can measure joint power in watts, just like we can any other work time relationship, right? It's just power, okay? How quickly are the joints being moved in a certain amount of time? Single gait cycle, right hip, knee, and ankle. Power generation is positive. Absorption is negative. Now that's really interesting. I think that's really neat, and that can give us a really good idea of how the body works. If you go back to some of the things that we talked about earlier in the semester, where we talked about that mechanical model of muscle, and we talked about concentric and eccentric contractions, and how we get that length tension relationship. And if you start to think of the muscles as this elastic organism with a machine inside of it, which are the sarcomeres, the myosin and actin, and how when a muscle stretches out and the sarcomere is still active, we create this big spring-loaded mechanism. And we have muscles on both sides of a joint. You have your knee joint, for instance. You have these muscular mechanisms on the anterior side, that would be your quadriceps, and the posterior side would be your hamstrings. So you have these two muscle groups that work in combination with one another. And depending on where we're at in the gait cycle, the knee joint might be in a force absorption stage or a force production stage, right? Force generation versus force absorption. More often than not, when we're talking about force absorption, we're talking at least one muscle group is in an eccentric contraction. Remember, potential energy and kinetic energy. And when we are in an eccentric contraction and we're really loading up a muscle group and the muscle is being stretched in an eccentric, we're loading up lots of potential energy that can be released later into kinetic energy. So I want you to kind of peel back in your brain a little bit and think about those relationships, okay? When we start talking about power in a generation of power or absorption of power. We can go through this graph here. You can obviously go through it on your own. I think it's really good practice for you to go through this graph on your own and kind of look at, okay, where is joint power generation happening? So when we get to toe off here, we have a lot of joint power generation at the hip. Where are we seeing a lot of generation? Where we're seeing the biggest? Look at this right here. The ankle really kind of absorbs a lot of force, which you would, if you look back at your previous graphs, if you take all the graphs that we've gone over here and you look at the joint angle, you would be in more than likely, or I know for a fact, you're in dorsiflexion right here, and then we're into big, huge plantar flexion. Look at the amount of power. And so why do we see this huge spike here at the ankle versus you see some spikes at the knee and the hip as far as force generation goes. When you look at the ankle, remember a couple things about the ankle. Well, one thing in particular about the ankle, it is a second-class lever. Knee is a third-class lever. Hip is a third-class lever. The ankle is a second-class lever. And what type of lever is the most able to produce force in a short period of time? That second-class lever. So, and that is a good thing, because when we're looking at toe off, right? When we're looking at toe off right here, you are putting out as much muscular force as you can with that gastrocnemius and that soleus to essentially push your body up into the air so that you can transition over to the next leg. It is close to Easter. Egg, leg, whatever. So that is something to keep in mind as far as how joints generating power and absorbing power are a really big deal. And I would bring your attention up to here to this butterfly diagram. And what this represents is the amount of force that's going into a force plate. So as somebody walks over a force plate, right, as their heel strikes into the ground, there's a ton of force, right? A ton of force that peaks up into that heel strike. And then we're starting to go into some force absorption, right? As we start to rock over our flat foot and we go into that single support and that stance phase, right? And then we start to roll back over to toe off. So that second class lever in the ankle is starting to really rotate forward, big toe off, big second class lever activity. We're putting a ton of force into the ground. And then obviously we rotate over to the next leg. Now, what about muscle activation? So we've looked at joint torque. We've looked at joint power. What about muscle activation? And this would be measured by the EMG, right? The electromyography, right? Those electrodes that are hooked up to the certain muscle groups. So as we start breaking down the gait cycle, right? And we start to look at, let's look at some different muscle groups here and see if we can figure out what's going on, right? We have the description down here. Typically, typical activity of major muscle groups during the gait cycle. It's going to say, kind of runs off the page, but abbreviations, it's telling you that the abbreviations here match up with this diagram over here. So what about the gluteus maximus at initial loading response, right? This makes sense, right? At initial contact, glute max, that makes a lot of sense. What is glute max responsible for? Hip extension, right? So as we start to land on the ground, we have that initial contact, we're going to want to extend our hip to start to stand up on that leg that we just landed on. Iliopsoas, that is our psoas major, that's our hip flexor. So that really isn't active until we start getting into swing phase. Why? Because we have to pick up our leg. We have to pick up our leg to swing it through. We have to flex at the hip. Hamstrings, we see hamstrings a little bit active over here. These are responsible for flexing the knee, right? Flexing the knee. So when we start to get into the later half of the swing phase, and when we start to rock over that leg when we first make contact, we start to see some initial activity of the hamstrings to help control for flexion of the knee. Quadriceps, quite a bit of activity when we first make contact with the ground, right? So remember the quadriceps are making sure that our knee stays extended so we can roll over the top of it. When are we going to see extension again, right? We're going to see extension again right before we start to go into swing phase. Then we pick up our leg, and then you can start to see hamstring activity starts to get in a little bit there. Now, the big one is triceps surae. What is triceps surae? You should Google that, right? You should Google that right now. If you don't know what that is, triceps surae is a fancy name for the gastrocnemius and the soleus. Those two big muscle groups together are called the triceps surae. And obviously, you can see that as we start to ramp up to toe off, right? To toe off with the leg that we're looking at. So toe off, you're going to be huge electrical activity in that triceps surae, those two big muscle groups. Then tibialis anterior. Tibialis anterior is the opposing muscle group or the antagonist muscle group to triceps surae. It is on the front. It is our dorsiflexor. It's the muscle group. Tibialis anterior is the muscle group that allows us to dorsiflex. So when we first land on the ground, we're in big dorsiflexion. When you're going into swing phase, you don't want your toe to be dropped down. You need to make room so that your foot passes over the ground and is ready to drop onto the ground. So we have big dorsiflexion here. And as we get into the swing phase again, you also see that muscle needing to pull the toe up so we can swing the leg through. That's tibialis anterior. Now what we have here is some force plate analysis of ground reaction forces. So remember Newton's law, for every action there is an equal and opposite reaction. So whatever force we put into the ground comes back up on us. Now we'll talk about running later in a later lecture and how those huge ground reaction forces can be used to absorb and store energy for potential energy later, or they can act on our skeleton and be really, really harsh. So if we look at we have our phases of the gait cycle, right? And we have a couple different things that we're looking at. Lateral activity of the foot and ground reaction forces associated with it. So we're looking at the foot in particular, and when it hits the force, the force plate. Gotta stop talking so fast, right? Okay, so when the foot is, I'm going to turn to the side a little bit. When the foot is on a force plate, there are a couple things you can measure. You can measure the lateral, the side to side, right? The side to side activity, right? That would be lateral. Fore and aft. Fore and aft is fore is ball of foot. Aft is the back of the foot. So how much pressure is being applied at the front and back of the foot, and then vertical, like just straight down to the ground. Okay. So let's go ahead and take a look at this here. One of the biggest things we want to pay attention to here is vertical ground reaction force. During initial contact, if you look at this, here is that butterfly simulation that we talked about a couple slides ago. If you look at that initial contact, that's your heel strike. You get a huge vertical ground reaction force, and then some force absorption that's happening as you start to rock over into that single support with your right leg, right? And then we come up to toe off, big force absorption, and then back, and then we are swinging now. We're swinging this leg, so obviously there's not a lot of force happening in the force plate with this, and then we come back over to the left leg, and it goes through the same cycle. Now, we spent a lot of time so far talking about forces and variables that have to do with the legs. But what about the arms? Remember that angular momentum is always conserved, right? Momentum is always conserved, linear or angular, doesn't matter which. It's always conserved. It's never lost. So when one part, I got to plug in my computer here, sorry. When one part of the body is swinging, then another part of the body must swing in order to balance out the body. If we were in outer space and we took a step, basically swinging a leg forward to take a step, what would start to happen is all that momentum would be transferred and we would start flipping. And we'd probably start spinning as well, because there was no friction, there was no opposing force from another part of our body to slow us down. On Earth, what happens is when you swing one leg forward, the opposite side of the body, so if I'm swinging my right leg, my left arm is going to swing forward to balance everything out. so that I don't lose my balance, and so that I maintain a nice, even gait pattern forward. Everything is balanced. And if we look at this study, this is really cool. I like this a lot. What happens if we start to modify how the arms work when we're walking? So you have someone who's walking normal, right? We have someone who's had their arms tied at their side. We have someone who's holding their arms at their side, and someone who's walking anti-normal. This person is actually, what they're doing is they're walking ipsilaterally. What that means is as their right arm goes forward, so does their right leg. So same side arm, same side leg. And what they did is they measured their metabolic rate. So they used watts per kilogram, right? So you could also have done this with VO2 as well. And which used more energy? Well, interestingly, walking same side arm, same side leg, not opposite arm, opposite leg, but same side arm, same side leg. You should try it. Expended the most energy. It was the least efficient, whereas walking normally was the most efficient. Tying someone's arms right to their sides makes them less efficient, and then holding your arms to your side. Why was this a little bit higher than this one? Well, they were having to really focus on using muscular contraction to hold their arms to their side. They didn't have like ropes doing it for them. If you think about this, if you've ever been in a swimming pool, for those of you who are swimmers, and you stick a buoy between your legs, and swimmers actually do this as a training purpose. They hold a flotation device between their legs and they just swim with their arms. The purpose of that is to just do upper body training and to make them very, very strong and pulling through the water with just their upper body. They can also use it to teach themselves how to turn more effectively in the water. When they reach for their stroke, they roll their body a little bit so they get really effective at rotating their body through the water. When you hold your legs together around that flotation device, it actually starts to make you rotate more. Because even in the water, even when you're swimming, if you stroke forward with your right arm, your left leg is going to want to drop to kick the water to balance you out, right? So no matter if it's in the water or if it's on land, if you start modifying how your arms work during the gait cycle, it's going to cause more than likely some over-rotation from your body. If you try walking with just your arms, you're going to have to rotate your body because you're swinging your legs. Like when you start swinging your leg around in that swing phase, right? And you start bringing that leg around, it's swinging and you're sort of rotating your body. So if you don't counter rotate, you're going to start losing your balance, right? So that's where the role of arms during walking comes in. So now we're going to start digging into the gait cycle in detail. We're going to take every single one of these piece by piece and talk about them, all right? So when we assess the gait cycle, again, just a reminder, we're looking at just one leg in particular, right? And for our purposes here, it's going to be the right leg as someone walks through the gait cycle. And then here is the gait cycle with a little bit more detail with some of the associations with the legs as we move through the gait cycle. Still the exact same thing, just a couple more added bonus concepts here, such as feet adjacent and tibia vertical during that swing phase. Things to keep in mind. A reminder that we might see some terminology here that has to do with moments, right? Just remember that when we say moments, we mean torque, all right? Torque at the joints. So let's start with initial contact, right? We're in initial contact. We have a loading response of ground reaction force, right? The heel strike changes in the direction of, there it is. So we initially get a heel strike, right? We've gotten a heel strike and we have dorsiflexion at this point in time. The hip extensor moment, right? The hip extensor moment, knee flexor, and dorsiflexion moment, right? These are all meant to control as my leg lands. And if we think about it in just a little bit more detail, right? If we think about it in a little bit more detail, as the leg we talked about this a little bit already, as the leg hits the ground, right? As the leg hits the ground, if we didn't have opposing muscle groups, everything would buckle. It would just fall like a loose spring or a worm to the ground. So we have to have those hip extensors. We have to have your glute max and everything sort of turn on to oppose the torque. We have to have a knee flexor to turn on. So remember, your leg has come through, it's swung. How do you slow that down? With your hamstrings, right? Your hamstrings operate like this to pull the leg backwards. So if the leg is swinging through, your hamstrings become a braking mechanism. And then you have dorsiflexion, right? Dorsiflexion to get your foot ready and to provide that position for initial contact, right? So if you want to think about it, the ground is pushing your bones and joints one way. When you make that initial contact, you hit the ground, and there's ground reaction force that goes the opposite direction, right back up on you. And what it's trying to make you do is this, right? So what opposing muscle groups help to stop that from happening? Hip extensors, knee flexor, dorsiflexion. Now we go into the loading response. Now, what's happened during the loading response is we've hit the ground, and we are now entering plantar flexion. So when the ground hits your heel, boop, it starts to rotate. The ground has hit your heel. The ground has hit your heel, so boom, and then it starts to rotate over, and now your tibia and your fibula start to come forward a little bit. That's why it's called the initial rocker, right? Ground reaction force in the trunk at its lowest position of center of gravity. That means you have hip and knee flexion, right? So you've landed on the ground, right? And you rotate down and your body sinks down just a little bit. So your trunk is at its lowest position of center of gravity. It's closest to the ground as it will ever be during the gait cycle. And again, it's called the initial rocker phase because when your heel has made initial contact and now it has rocked forward and it is parallel, it is touching the ground. Ankle plantar flexion is controlled by the dorsiflexor. So many words. Now, this is a big deal. As we hit the ground and we get that initial rocker, right, where the ankle rocks forward, what makes that a smooth motion? Tibialis anterior. Eccentric contraction of tibialis anterior, right? As my foot comes down, I'm going to start getting plantar flexion with my gastroc and my soleus, or that triceps surae muscle group back here. I'm going to get eventual plantar flexion. But as I go into the initial rocker, I'm coming from dorsiflexion. I'm going to plantar flexion, and I'm going to get more later. But in order for this to not, bam, slap the ground as super hard, it needs to be a smooth transition from this dorsiflexion into this initial rocker phase, and that's tibialis anterior. Eccentric contraction. It's a braking mechanism to slow down from dorsiflexion into that plantar flexion where we get flat with the ground. We still have hip extensor moments and knee extensor moments controlling that opposite torque so that our knee doesn't buckle and our hip doesn't buckle. So if I'm talking about the hip joint, if I don't want my hip to buckle underneath me like that, what do? Contract my glute. So go out and do some walking and kind of think about it. As you first hit the ground and you get into that loading response, you're taking all your body weight and it's starting to rock over to one leg. And in order for you not to fall down, if you flexed your hip, you would just go straight to the ground like a squat. You don't want to do that. So you have hip extension, knee extension moments occurring. So loading response, opposite toe off. Now, as we start to look at this phase here and here, what we're starting to see is we have come through a double support phase, that first 10% phase of stance, and now we're moving into our first period of single support, right? Our first area of single support. So that left leg is starting to push off. Our foot is flat, completely flat on the ground. We have our pelvis starts to twist backwards and our trunk starts to gain height. Now that's important. So when you walk, you have to imagine that as we walk, you look at the pelvis, right leg forward, left leg forward, right leg forward, left leg forward. Now you don't see this like, in some people you can actually see it happen quite a bit. Some people have really rocky hips, or some people have hips that rock side to side quite a bit, right? So right leg forward, left leg forward, right leg forward, left leg forward. So as we start to reach forward, in that initial contact period, we have the pelvis is kind of open a little bit, right? We've reached forward with the right leg, and the left side of the pelvis, this is my left leg, will be twisted backwards a little bit. And as we start to get into this opposite toe off, this loading response, right, where the foot is flat, we start to rotate the pelvis forward a little bit, because we're going to have to bring that left leg forward, right? Left leg is starting to toe off. Left leg is starting to toe off, and we're going to have to rotate it forward, right? So the first thing, we got the right leg forward, and then the left leg is going to have to follow behind, and that's where it says the pelvis starts to twist backwards, starts to twist back into its neutral starting position, right? And we start to gain height. If we're right here, what's happening? Now we're starting to get some hip extension, right? With some positive concentric contraction of the glute max. We're starting to stand up more on that leg. Our center of gravity is starting to rise upwards. And initially, when we landed, remember, when we got flat on our foot, your tibia and your fibula kind of float forward just a little bit, and now they're starting to go back, and we're starting to get ready for plantar flexion with the soleus and the gastroc to really, really get us through mid-stance and get us to toe off. So now we've entered that mid-stance phase, and we have that the swing leg, which in this instance is the left leg, right? We are in stance phase with the right leg. So the swing leg has passed the stance leg, right? And we can see that we passed opposite toe off here, and we are getting ready. We are getting ready for the heel raise component of our right leg. Ground reaction force anterior posterior component is near zero. What does that mean? That means that the foot is pretty much equally balanced. So the tibia and the fibula and the body weight is equally balanced straight through the foot. There's no more weight on the front of the foot than there is on the back of the foot. It's equally distributed straight down. The trunk is at trunk's highest point, right? This is the highest point that you will be at here in this mid-stance phase, right, until we get into toe off. And then we have decrease in hip extensor moments, right? Decrease because we're getting ready to go into a swing phase where we're going to start flexing our hip. Large muscle activity in the frontal plane. Now that's a big deal that we need to talk about, right? During this swing phase, there's lots of frontal plane activity, and we're getting ready to enter the swing phase, right? I'm sorry, let's back up. You are technically in a swing phase here, only it's not for the right leg. Anytime you have one foot off the ground, you're going to see a ton of frontal plane activity musculature, all right? I got a couple notes off to the side here. So if I'm on one leg, I have my obliques, right? My glute max, my glute med, and my glute min. And the goal is, when I'm on one leg, to keep me that way. And when you're on one leg, there's a ton of frontal plane musculature activity so that you don't tip side to side when you start swinging that opposite leg through. So when I'm in stance phase and I'm in mid stance over my right leg, right, the abductors and the adductors are working really hard in the frontal plane to keep things balanced. Now we're working from mid stance to the heel rise component, right? We've gotten through mid stance and we're about ready to see this heel come off the ground. You're going to transition from mid stance to the terminal stance. You're going to start hip flexing, right? You're going to start, so here we are at the most extension that we're going to have. So you're going to start to flex the hip. Why are you going to start to flex the hip? You're going to start bringing the knee up so that you can swing that leg through. And you're going to start knee flexing, increasing plantar flexion, right? You're going to put that toe into the ground and you're going to stand up. Terminal stance, right? It's about 50%. We're about halfway through the gait cycle here. So a terminal stance, we're going to see our terminal rocker push off, right? And what is a terminal rocker push off? Your terminal rocker push off is the opposite of initial contact. So we've been flat on the foot, we've rocked over the foot, and now we're doing our push off, our toe off, to get ourselves to push off of that right leg that we've come through stance phase. And now we're starting to see a reversal of the torques. Now we're going to start seeing everything, instead of being in extensor moments, we're going to flexor moments. Why? Because we need to start, we're going to have to start, look, we're going to have to start flexing the knee. We're going to have to start flexing the hip to be able to clear the ground as we swing through. So we're going to start the acceleration of the limb forward into the swing phase. Now we are in pre-swing, right? We're about 60% of the way through the gait cycle here. So we're starting to move into pre-swing, would be the beginning of the swing phase, right? 60% of the way through the gait cycle. Hip flexor moments cause the knee to extend. Hip flexion causes the knee to extend. What does that mean? Well, we're going to start flexing the knee. We're going to start flexing the hip, right? We're going to start flexing the hip, and it's probably easier if I show you on myself first. If you flex the hip, you start to flex the hip, right? That brings your knee forward, doesn't it? And if we start to flex the hip, it's going to start to swing. Remember, it's swing phase. So if I start to flex the hip, the lower half of my leg, I'm bringing my leg up, it's going to drop and start to swing forward. That's why it's called the swing phase. So as I start to flex that hip, right, I am flexing the hip upwards, and the lower leg starts to swing. It says knee extensor moment to limit flexion, right? So we have this right here. We have a knee extension at the quadricep, right? So we're starting to reach out in front of us, right? Or we're starting to prepare to do that, right? We're starting to get ready to do that. So we're starting to increase that muscle activity in the pre-swing. Now we're into that initial and mid-swing area, right? We're into that initial mid-swing. We're right here, right? So we are having the swing leg, which again is the right leg. It starts to pass the stance leg. So it starts to pass that left leg, and we would be in this area which we would call feet adjacent, where the feet are lined up with one another, or they're passing one another. The swing leg is passing that left leg, and the feet are right next to each other. We have foot clearance. This is the point in time where you're swinging your foot, so you're going to start preparing. You don't want to leave your toe down here. You're going to start preparing a little bit, right, with some dorsiflexion to start getting your foot clear from the ground. you're going to have hip flexor moments. Elevate the hip and swing forward. So you're going to bring your hip up so you can swing that leg forward. There's going to be a small knee extensor moment to limit knee flexion. So what would make a walking gait really inefficient is if we bring our heel all the way up to our butt. Okay? So you don't see people walk with their heels that go all the way up to their butt. That would be really inefficient. So in order to make sure that you don't flex your knee too much, knee extensor or quadricep activity turns on just a little bit to make sure you don't throw your leg too far up close to your butt. Now we're into that mid swing and that tibia vertical. So now we're past feet adjacent. We've gotten to tibia vertical. So now we're at a place where the tibia is vertical or perpendicular with the ground. We're about 86–85% of the way through the swing phase, through the gait cycle. Through the gait cycle. We are going to get now we're going to get those hip extensors to turn back on. Those hip extensors, right? So if this is my pelvis, right? If my pelvis is, get this here. If my pelvis is swinging, that's better, right? If my leg is swinging forward, what can I do to control that? I can get some gluteus maximus, right? Some posterior hip muscles, my hip extensors, right? Hip extension is this, hip extension, hip flexion. Hip extension, hip flexion, right? So if my leg is swinging forward, how can I control that? Hip extension, the opposite torque. What's going to slow it down, right? So if my leg is swinging forward, I want to slow that down and get some hip extension. Knee flexor, same thing. If my leg is starting to swing out in front of me, right? If my leg is starting to swing, right, through this mid to terminal swing phase, how can I slow this leg down? I need some hamstring activity back here to start providing some torque to sort of slow things down, and that would be an eccentric contraction. And then obviously our very last terminal phase is just the terminal phase of swing is 100% of the gait cycle has been completed, and we have one full stride completed, heel strike to heel strike. Now, a couple other things that we'll talk about here, some other little things that you can talk about with gait is one is heel strike transient. Now, what this heel strike transient means is how large of a spike do I have when I make initial contact? How much force am I absorbing? And if you remember when we talked about potential and kinetic energy and force absorption, we talked about using that plantar fascia and the arch of the foot as a force absorber when we land, right? When we don't use that mechanism very well, and this goes for a lot of people, especially some older people who don't have great control of the knee joint, what will end up happening is they'll end up landing like more fully extended and bam, land right on their heel. And you get this big, huge impact transient or this huge return on ground reaction force, this big spike, right? And then they go into that initial rocker phase, and then they start pushing more into the ground as well. And then they get to heel strike again, bam. And you can see that it has to do with the position of the foot at the heel strike, right? Absent impact transient is when someone lands on their foot in a more efficient way, when they can use that, I guess I forgot to put my, here we go. When they can use that natural force absorption mechanism, that spring-loaded mechanism, instead of landing right on their calcaneus of their heel. Now, we talked about using force plates earlier, and this slide talks about center of pressure. Where is the center of pressure of the foot? Especially as the foot is moving through that initial stance phase, and we're getting into that initial rocker phase where the foot travels from heel impact or back of the foot impact all the way through the front half of the foot to toe off. When we look at the center of pressure, we can look and we can see a few things. Where is there abnormal foot contact on the force plate? So we know that most people should have a center of pressure that sort of follows a fairly curved line, right? We start with the outside of the heel, and then we end up with the inside of the ball of the foot. If there are abnormalities there, that might have to do with some diminishment in gait capability that could be connected with a clinical issue or something like that, right? A lot of times when they do analysis on this, they will combine it with an outline or a tracing of the foot as well. That's center of pressure. This is kind of a summary of something that I said multiple times throughout this lecture. And it has to do with support moments and opposite torques. So when we look at the sagittal plane and we break down the human into the joints into just a spring-loaded machine, and you look at these arrows represent torque. And so if we have the quadricep torque here, we have the hamstring torque here. So the hamstring wants to flex the knee, and the quadricep wants to extend the knee. Every single joint, the hip, the knee, the ankle, works with two muscle groups on each side. So if we start the ankle, we have tibialis anterior out front, dorsiflexor. And we have triceps surae or gastroc and soleus on the back, plantar flexor, right? Then if we go up to the knee, the huge quadriceps group of musculature, hip extensor. Then we have on the back side, we have all the hamstring musculature, hip flexor. Then at the hip, if we go up to the hip, if we surround the hip, on the front half of the hip, we have the psoas major, right? On the front of the hip, we have psoas or iliopsoas. That is a hip flexor. And then we have a ton of hip extensors on the back, gluteus maximus being one of them, hip extensor for glute max, and then iliopsoas and psoas major, psoas minor, hip flexor. So you have to imagine that as one part of the joint is moving into extension, if the knee is moving into extension, then we know that the hamstrings are also applying a torque to try and control that extension with a flexion moment or an eccentric contraction at the hamstrings. Hopefully you enjoyed the gait analysis section. It's one of the cooler sections where we get to start applying all the variables that we've talked about so far in class. If you have any questions, please let me know. Have fun.